Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So today is another lecture where we will continue with the material we dealt with on Faraday's law and Lenz's law, which both deal with this idea called electromagnetic induction. And so now, electromagnetic induction is extremely non-intuitive. It is, not something you would expect to happen in nature, but yet it does, and it can be intuitive too once you understand what's going on. Okay, so that's why you should pay a lot of attention in understanding this material. Okay, so so let me get going with our, little bit about our product, etc. We offer the two platforms for NEET and JEE, Sushruta for NEET and Ramanujan for JEE. And these two products, you can try them from YouTube by going to play.google.com and looking for com.JnanaMarga.Sushruta. Download it there, you register, and once you register, if you have any problem with registration, you contact support@JnanaMarga.in. Okay, support@JnanaMarga.in. Now, if so you go to the Play Store on your cell phone, Android phone. The Android phone does not work on iPhone. Go to or on a tablet, Android tablet, download the app, and then and then install. And once after installing, you look to register. Once you register, you are in, and you will see a screen like this. And from this screen, you can study whatever material you want to help you prepare for your exam. The other product, of course, we have our second flagship is the Ramanujan. The Sushruta is for the NEET students, as you know. Ramanujan is for JEE. Same story. You go to play.google.com on your cell phone, then look for com.JnanaMarga.Ramanujan, and there you look to download and then register. Okay, so now both are available for free download. Okay, now and this is the best programs that you can buy. As of now, the pricing is 11,000 rupees for 1 year, and this can help you immensely. These lectures that I am conducting, they are actually free, but they go along with your program. One of the new things that we have added is assessment. Assessment will go a long way in helping you self-assess. What you need to do once you learn the material, right? You should self-assess, and the best way to do self-assessment is using our app. You go, you click, you do some problems, and then you build confidence around the material. So having explained these two things, this is what you should do. We also have Jnana Test Prep. Jnana Test Prep, you can start attacking whole tests using Jnana Test Prep once you are ready. Okay, so please get yourself ready for that. Okay, so now we started looking at Faraday, right? Faraday discovered this idea of what is called electromagnetic induction. Okay, so what is electromagnetic induction? We already explained. There was Faraday's experiment. He had an iron ring which had two circuits. One was connected to a battery, and the iron ring is called a torus. We have toroid and solenoid, right? The toroid is a circular ring, and what he did was, on one side he wound a full circuit which he attached to a battery. On the other side he had a ring which he attached to a measuring ammeter. We already looked at how ammeter and voltmeter works in the context of the previous chapter, magnetostatics, right? Now today we are looking at now what did he see, right? When he turned on the circuit, he found that the ammeter or galvanometer would flicker, and it happened every time he turned on the circuit, but then it would come back to normal. Okay, and so what was the cause of that? Okay, the cause of that is, why did it flicker and then turn back to normal? We said that it is because of what we called was the idea that there are currents induced in the second circuit. Notice that there is no battery in the second circuit. The idea that there are currents induced in the second circuit, right, with the ammeter, right? There is current induced in the second circuit with the ammeter due to the magnetic field created by the first, right? If you all remember, we had two laws, right? In the previous chapter in magnetostatics, the first law was that a current carrying conductor in a magnetic field, right, will experience a force I times L cross B. So current carrying conductor experiences a force, right? The second idea that we found, or that we learned, was that a current carrying conductor also creates a magnetic field around it, right? So now, in this case, the second law, which is Biot-Savart's law, is what comes into play, right? And then we looked at the induced fields in various situations, right? So now, in the first circuit, right, when you turn on the switch, there is a current flowing through the conductor, right? Now that current induces, that current produces a magnetic field in the ferromagnetic substance, which is the iron ring. We looked at magnetic materials also, right? Now, so it produces a magnetic field in the iron ring, which in turn induces a current, right? So after the first part, everything you did was dealt with Biot-Savart's law, right? That a current produces a magnetic field, right? Now the magnetic field that is produced by the first loop, which is connected to a battery, right? That current produces a magnetic field. That magnetic field induces a current in the second closed loop. Okay, so if you had a closed loop in a magnetic field, right, it induces a current. But what happens in the galvanometer is it does not move to the side and stay there. No, it moves and comes back to zero. So it produces an instantaneous current in the it produces a current for a short period of time in the second loop. Okay, and that is what is detected by the galvanometer. So what Faraday said was that induced currents, right? There is an induced current through a varying magnetic field. Okay, so if there's a varying magnetic field, then you experience an induced current. So current is induced in the second coil due to a varying magnetic field. Okay, now if you move a magnet near a coil like that, right, you have the same thing. The faster you move it, the greater the current that is generated. Okay, so the varying magnetic field is what causes the induced current. Okay, so moving in front of a magnet, right, and if you do this, the bulb will always light up. But if you look at it with a galvanometer, as you do this very, very fast, it will go back and forth, back and forth, back and forth, because when you move it this way, right, it produces a current this way. When you move it that way, it produces a current that way. Okay, and this then led to what is called as um, um, Lenz's law, which is a law along with Faraday's law. Okay, so but first let's explain what Faraday did say. The induced current is proportional. Faraday's law states that the induced electromagnetic force, right, is which is due to the magnetic field is proportional to the rate of change of flux d phi by dt. Flux is magnetic flux. Magnetic flux is the closed integral of B dot dA. Okay, so if you have a field in this direction and you had an area like that, if you had an area like this, the direction of A, you know, is this way. So the B and the A are parallel. So B dot dA will have a proper flux, right? So d phi by dt will then produce u. So integral B dot dA is phi. D phi by dt equals EMF, the voltage that is produced. Okay, so we all know that EMF is also the line integral of E dot dl, right? And therefore we ended up with Faraday's law. Okay, so now this was just a recap. What Lenz's said is that the direction of the current produced will be in such a way as to oppose the changing flux, right? Because now this current will produce a magnetic field. That field will oppose the flux, the changing flux. Okay, so that is the critical idea there. It's not a simple idea. You have to understand it, and you have to understand it well. You must be able to solve problems in this context. D phi by dt equals V or EMF. That EMF is also measured in volts. Okay, so now having explained the electromotive force that is being generated, and explained the changing flux, the closed integral of B dot dA, and then the time varying nature of it, right? We end up with this law. Okay, so now the so you end up with what is called an induced current, and the direction of the induced current changes. When you go this way, the direction of the current goes one way. When you go this way, the direction of the current goes the other way. Okay, when there is a changing magnetic field, leads to an electric field and the current induced in the surrounding coil. Okay. So this is the basic idea of generators and other electrical implements like generators, like for instance the dynamo in your cycle. Okay, so and then when you look at it, you must find the B, and then you must find the A, right? And then you have to multiply the two, B times A or B dot dA, and if there is an angle between the two, then you must use that BA cos theta also, and then so that will give you that. And then if you need to find out which is changing, right? Whether it's the area that's changing or whether it's the B that's changing, and based on that you will produce a EMF. And once you have the EMF, then V by R will give you the current. Okay, so then we discussed the solenoid, and then we discussed a solenoid which is inside another solenoid, right? So here there are two solenoids, S1 and S2. You have a current in one which produces and induced electromagnetic field, right? And and then that the inner solenoid, let's say you had a varying current in the first one, it will produce a varying field, and when that varying field in turn will produce a current in the second coil. Okay, so that's how this whole thing works. Okay, so induced EMF is mu naught Ni times pi r squared di1 by dt. Okay, so the flux is phi equals um, um, here B dot A is mu naught Ni pi r square. Why is it mu naught Ni pi r square? That we already discussed. That mu naught Ni, you use what is called Ampere's law, right? With respect to the solenoid, the magnetic field within the solenoid is mu naught N1 times I1. N1 is the number of loops, that is number of turns, right? So the turns per unit length gives you the is N1. So the magnetic field within S1 is mu naught times N1 times I1, right? And so now mu naught times N1 times I1 is B, and B times A is the area. If you had a the radius of the outer solenoid is R2 square, or the radius of the inner solenoid is R2 square. So because we are interested in the magnetic flux per turn in the second one. So B dot A on the second one is mu naught Ni times pi r square, mu naught Ni times pi r square, and that will give you the B dot A, the flux, and d by dt of that is di by dt, because I is the one that's changing, and therefore if you had the current changes from 1 to 0 in 10 milliseconds, then you will have di by dt equals something, and then a corresponding EMF. Okay, so this is a rough question. Remember, there must be a changing current to produce a changing magnetic field. Okay, so keep that in mind with respect to induced currents. Never forget the di by dt. The need to have a time varying magnetic field. All right, so d phi by dt equals EMF, induced negative d phi by dt, negative EMF. Okay, so now the changing flux due to the motion is called a Lorentz force, and then we looked at the Lorentz force is q times qvb, right? If you remember, equals eq, right? And so as a result, we ended up with E equals VB, and therefore E times E times L was the EMF. The EMF divided by R was going to give you the induced current. Okay, so so in this case, the magnetic force on the moving conductor was I times L cross B, and therefore you had B square L square V divided by R, right? So was I times L cross V. I was VBL by R, and therefore you had B square L square V by R. Okay, so now the work done is the force times the velocity, right? And the force times the velocity was therefore magnetic force was B square L square V by R times V, and therefore that produces you the power, right? F dot V is the power, or I square R is the power. Okay, so so the rate of change of flux in this kind of situation where you are doing moving this a third rod in a magnetic field at a quick rate, right? The B is changing. It is not the B is changing because the area is changing, right? It doesn't matter. The B is not changing. The B is constant, but the A is changing, right? So the flux is B times A. In this case, what is changing? X is changing. So and the rate at which you pull this is the area. The area is changing when you pull that, right? So because the area is changing, your total flux is changing. As a result, there is a induced EMF. So if you kept doing this and that, it will also produce a current. Okay, but you need to keep doing this and that in order to produce that current. Okay, so then we discussed eddy currents, and we brought eddy currents are currents that are induced, right? And inside a plate or a thick material due to these induced currents, and this leads to heating up of the material, which means there is a wasteful use of energy. So they instead of having one thick wire, they had many thin multiple wires, or they ended up with many laminations of a particular coil, which stopped the currents from going across each other, but they were there to produce a laminated material which had far fewer eddy currents. To reduce the effect of eddy currents, here also they created a sawtoothed pendulum in a moving magnetic field, and therefore you ended up with pieces. Okay, so eddy currents are used in braking in trains, induction furnaces, and basically heating is undesirable in transformers. Okay, so therefore we came up with this idea of mutual inductance when there is a common inductance. Introduces a current which is produces a flux, right? If there is one loop in which you have a changing current, it produces a flux in the second loop, and the common idea was that the induced flux was proportional to the current in the first one. The induced flux in the second one is proportional to the current in the first one. So phi2 equals M21 times I1, and the M was common whether you put the current in this side, and it led to an induced current in the other side, or induced EMF in the other side, or whether you put the current in this side, which led to an induced current in the other side. Okay, so now when it comes to transformers, basically it is the ratio between the number of loops which then decides whether the voltage is stepped up or the voltage is stepped down. So that is the idea behind mutual inductance. And therefore mutual inductance, when you have one inducing the current the other, and later on you change and pass the current to the other one, it will also induce the current the first one. So then you will find that this mutual inductance is the same between the two, regardless of which side you pass the current. Okay, so phi equals mi, phi2 equals m12 times I1, or the other way around, m12 will equal m21. Okay, and therefore the induced flux will be proportionate to this, will involve the same constant. Okay, so if you had the same current, you will have the same flux. Okay, so much for that. So that was this idea of what we called mutual inductance, which was called M, which is given by this formula mu times Ni, if you remember, was the magnetic field, and mu times Ni was the magnetic field, times pi r1 square would give you the field in the other one, right? And based on that, we then calculated that you ended up with the same flux. Okay, so so M12 was equal to M21. Okay, so now let's move on. If you produce a field, it would then produce M times di1 by dt. Okay, and there was a common M. Okay, and that common M was mu times n1 times n2 times pi r squared times L, right? So now we then come up with this idea of what is called self-inductance. I produce a changing field in a solenoid, right? It will then cause I produce changing current in a solenoid. It will then cause a changing. It will then induce a changing current as well. Okay. So the EMF is negative d phi by dt, and the phi is proportional to the incoming current, therefore phi equals Li. So the induced EMF will be L times di by dt. This is the most important I. Negative L times di by dt. This is the, for an inductor, this is the basic formula that the voltage across an inductor is proportional to the time varying current di by dt. Rate of change of current will produce a voltage, an induced a self inductance in the current, in the inductor. Okay, so L times phi equals Li, d phi by dt equals L times di by dt. Okay, and that is called self inductance. And normally when we talk of inductors, this is the formula we are talking about. Okay, so now in the inductor is the opposite of the capacitor. If you remember from our earlier material with respect to the capacitor, we said that Q is equal to CV and dQ by dt equals C times dV by dt, right? Now that formula, right, I equals C dV by dt. This formula is V equals L di by dt, right? So these two are kind of alternatives of each other. In one case, you integrate for the current. In the other case you differentiate for the current. So in the inductor, you differentiate for the current. In the capacitor, you integrate for the current. Therefore, these are used in circuits together. And very often what they do is they produce oscillatory circuits. And this is where we are headed now. Now the measure for the for L, right? L, which is the inductance, right? The self-inductance or inductance, as we generally call it. The measure for inductance is Henry, and therefore L is measured in Henrys. It has the same dimensions as V divided by di by dt, or as you know, V equals IR, right? So it is in some ways related to, if you look at ohms, it is ohms per time. Okay, so if it is ohms per second, it's something like that. Okay, so we thus ended up with two kinds of situations. One is the transformer, which is based on mutual inductance, where there is one loop and then there is another loop. You pass current through this loop, varying current through this loop, it produces another varying current in the other loop. That is a transformer. Then you had the self-inductor, where you had only one loop, so it induces a current in the same loop. You pass the current through it, it will then induce a current. Therefore, you have EMF equals L di by dt. And so now we then look at this, the self-inductance of a toroid, right? We already looked at the toroid at the beginning of this Faraday's law, where we used two loops through a toroid, right? So now in this case, we are only going to use one loop. Okay, so there's a toroid is completely wound, and then you pass a changing current through it, right? Now, what is the if you use what is that Ampere's law, B dot dl equals mu naught I enclosed, right? So then you use that 2 pi r times B equals mu naught Ni, right? N is the number of turns and I is the enclosed current. Therefore, you have B equals mu naught Ni by 2 pi r. Okay, so that is the how you look at the that is how you look at the Ampere's law in the context of the toroid, right? B dot dl equals mu naught Ni, and I equals, if you look at the there are NT turns, right, and therefore from that you had mu naught NT times I divided by 2 pi r. Okay, so now the magnetic flux that is induced inside, right, inside the toroid is B times A, and A is pi times little r, right? So in this case, notice the two r's, right? The big R is for the loop itself, and there is a little r which decides the, or in this case, the little r is for the big toroid, the radius of the toroid itself, and the A is the radius of that cross section. Okay, so the A here, right, is the pi r squared of this one. The 2 pi r here is the radius of the toroid itself, the big circle, right? This one is the pi A is the radius of the inner one. Maybe it's a square toroid, also. And therefore, correspondingly, you have to calculate and then use that to find the L, right? Phi equals Li, right? And therefore, whatever remains in phi equals Li is your L. Okay, so mu naught n square A by 2 pi r for a toroid. That's how you, and then if you need to find the EMF, it is L di by dt, right? And the work that, in terms of total work done in increasing the current from 0 to I is, what is the work done? It is the EMF times di, right? L, the work done is EMF v times I is the power, right? The V is L di by dt times the power, right? Times V times I, L di by dt times I will give you the power, and therefore, if you integrate over, how it takes a certain period of time for this power to go up, and therefore dW equals Li di. So you will end up with Li square by 2. Integrating both sides to drop the dTs. So V times I is the power, dW by dt is power. Therefore, you drop the the phi is L di by dt. Drop the dTs, dW equals Li di. Therefore, integrate both sides, you end up with W equals half Li square. And so that brought us to the energy stored is half Li square, and the energy density per unit volume is half B square by 2 mu naught, so take a look at that, half Li square, and then you use that to calculate the energy stored. So we already calculated L in the case of the solenoid, right? Mu naught n square pi r square L, right? Not that much different from the toroid, right? So from that you end up with the corresponding equation for the energy, right? Half Li square you plug in for L, and then you end up with the total equation for the energy. Okay, so with that, B square by 2 mu is the energy stored in energy density, and in the case of the electrostatic field, if you remember, it is also half epsilon E square. Energy stored per unit volume was half epsilon E square. In this case, instead of epsilon, you have mu in the denominator. So it is there is always the half. There is E square in one, and so that is the energy per unit volume. Okay, so and then we also now see today, what I wanted to do was, when the continue with this idea, then there are all these examples that, what I suggest is when you download our app, you kind of go and look at all this material discussed in great detail in the various IIT PAL lectures. So if you wanted to understand, non-uniform magnetic field in the context of, two concentric, a pipe like that with a hole in the middle, etc. Okay, so in those circumstances, you take a you go and look at how they do these integrations in the context of Ampere's law, and coaxial cable, etc. So I'm not going to go over the whole set of details here, and how these equations are derived in the context of Ampere's law, because I have to move on to a more important idea, which is the idea of the AC generator. Okay, now the the B and the A, right? So if you had a magnetic field, and in that magnetic field you rotated a coil, okay, and then there is an induced current in that coil. Okay, now how do you close that circuit, right? Often you can just close it using a transformer, okay, and then on the other side you will have a voltage that is induced because it's a transformer. Okay, so now what do? Keep two magnets, and in between the two you have a loop. Okay, then you rotate that loop like this. There are two magnets here, then you have a loop in the middle, and then you rotate the loop. As you rotate the loop, the phi changes. Why does the phi change? Because the direction of B changes. BA cos theta, right? So the angle theta is what is changing continuously. Okay, so when you are like this, B is like this, A is the direction of A is like that, right? So it is the direction of cos theta that is changing. So the A is like this, the B is like this. So cos theta is 90. Cos 90 is 0, right? B and A are perpendicular to each other. Therefore, the dot product is 0. The flux is 0 when B is like this and A is like this. A, remember, is perpendicular to the plane of the loop, right? Now, as you keep turning the loop, right, you keep in the flux that is induced keeps changing, right? And the flux that is experienced is changing in the loop. Therefore, the current that is induced, so there is an EMF which is proportional to that changing flux. Okay, so now because the flux is changing, right? Remember, because when you rotate it, there is a d theta by dt, right? And therefore, if you keep it rotating at a fixed rate, right, you have a corresponding d theta by dt, and therefore you end up with this BA, cos theta, right? d phi by dt will become BA sine theta d theta by dt. There is the minus also, and that minus and the derivative cos theta's derivative sine theta will cancel, right? So it will be BA sine theta d theta by dt. Okay, so you will have a induced EMF which is sinusoidal. Okay, and it's the rate at which it is rotating, right? The d theta by dt is happening, right? So what are we doing here? We're just taking d phi by dt, and we know phi is BA cos theta. When you take the derivative d phi by dt, it becomes BA sine theta d theta by dt, right? So you have a EMF which is sinusoidal with if you keep the d theta by dt constant, you will get a sinusoidal EMF, and that's what we call alternating current. Okay, so so that's why he draws this. Okay, so if you had a phi like this, cos theta, so this is the cos theta, you will have an EMF which is a sine theta. Okay, so you have two magnets, and in between two magnets you have a closed loop which is rotating. Okay, so as the closed loop rotates, you have an induced current in that closed loop, which is then connected to a circuit. This is how a dynamo also works, and therefore you end up with this BA d theta by dt, which is the same as omega and sine omega t, and theta is omega t. Okay, so that is the basic idea behind the generator. Put two magnets with the north and south pole, and in between the two magnets you have a coil which you rotate. So and there are two or three different types of generators. The most common is form of power that we have today is what is called thermal power. Thermal power happens when water is converted to steam using our good old friend Mr. Coal, or maybe maybe some places they use also natural gas. In the United States, they tend to use natural gas, but typically you have some kind of fossil fuel which then burns the water and converts it to steam. Steam at high pressure is used to rotate the coil, and as that it rotates the coil at a fixed rate, it produces some kind of motion, right? Exactly what you see in a steam engine, right? It's just a steam engine. Okay, so they took the same technology from the steam engine, which they used to generate, which they used to power the locomotive, the trains. The trains were powered by coal not so long ago. I have been in a coal train. Okay, so just like that, similarly, they take that, and what does it do? It produces rotary motion. The same rotary motion they use to turn the coil, and that turning coil then is held by, they will have some kind of graphite or some kind of brushes. Okay, and you touch those brushes, and they will always be in touch, and it will induce a current. These currents are then used to power the light, my laptop, and everything. Pretty much they are the source of utility generated power across the world today. Okay, so thermal power is what drives the AC and the bulb and everything else in most people's homes. Okay, now an alternate form of power is through the power of water. Many countries, including India, are are blessed with great rivers. The river Ganges flows from the heights of the Himalaya, down into the plains of India and to the sea. As many of you know, right? The Ganga, right? The dam that they have on the Ganga called a Teri Dam, produces, I think, almost a gigawatt or more of power, because of the height from which it flows. There are many Kosi River, many rivers which have, hydroelectric power in India. The other place where there is a lot of hydroelectric power also is the Bakra Nangal, which is which was made by Pandit Nehru in the years following India's independence. By 1960s, he had set up Bakra Nangal. They were generating power for the country. Similarly, in the 1990s, the Sardar Sarovar Dam was built, and along with that, they also generated electric power, which is now providing power to various peoples in the tribal areas of northern Maharashtra, as well as the cities that border it, including I think Ahmedabad. I'm not sure. No, so many places also get hydroelectric power. Yet the most common form of power is even today thermal power. You know, and in the United States, of course, we have natural gas. We have both thermal power, coal-based power, as well as natural gas. In what is that? Germany, they use tremendous amount of thermal power today. The third form of power is the power from nuclear fuel, which is used to generate, which is used as the fuel that produces that heats up the water. So nuclear fuel heats up the water, and then that then becomes steam and then powers the generator. Okay, so nuclear power is very popular in France. I think almost 80% of France uses mainly nuclear fuel, and also in Japan. Okay, so and then the final idea that we had to deal with is including the idea of this displacement current, right, into the equation for Ampere's law, right? Now, instead of B, they brought in this term called H, and this H also including, so B dot D equals mu naught I, they then included the second term, B dot DL equals mu naught I plus mu naught epsilon d phi E by dt. So this is to take into account the displacement current, which is produced, say, in a dielectric medium, which is different from the conduction current. When we normally talk about, a electrical circuit, we normally talk about V equals IR, which is what? Conduction current, right? Current produced in a, like say, a metal wire, right? Now, if you had a capacitor in that wire and you ended up charging that capacitor and then discharging that capacitor, it happens without the flow of charges through. There's no conduction through the capacitor. There's a form of what is called displacement current. Polarization leads to the current. Therefore, to take that into account, take polarization into account, they added this other term, mu naught epsilon naught, B dot DL equals mu naught I is Ampere's law, right? So then they added the second displacement current term into the Ampere's law as well. Okay, and therefore they call this Maxwell's modification to Ampere's law. And Maxwell, he recodified the everything that people had learned in electrical engineering over a period of time, right? We saw Faraday, before that we saw Biot law, before that we saw Ampere's law, before that we saw Coulomb, and then of course there is also this idea that you always need magnets always come with both a north and a south pole, right? So he recodified these laws into what are today called Maxwell's laws, and they form the basis of electromagnetic theory. Modern electromagnetic theory is built on Maxwell's laws, 4 laws. Okay, and we will go over the 4 laws pretty soon. But before that, first let's understand the addition that he added B dot DL because mu naught IC plus the second term, which is the displacement current term, which comes as a result of polarization in a parallel plate capacitor. Okay, what I suggest is, this is a very detailed discussion, but it is a discussion particularly if you are planning to be in engineering, or notably electrical engineering, which you should listen to when you, my suggestion is you listen to the detailed discussion on displacement current by tuning into the IIT PAL lectures. Okay, my aim is to kind of keep moving forward, so that we can make significant progress. Okay, now the flux, right? The flux that you see inside inside a medium, right? varies like this, goes up, right? B dot dl equals mu naught I, right? And on to outside, right? Because from 0 to r, there is the it is inside the medium. Okay, inside the medium, 0 to r, you have a linear variation. Okay, outside you have this it goes as an inverse law, right? Why is that? So you have the flux inside and the flux outside. Why is that? Inside you have a linear law 0 to r, because why is this? As how does it vary with respect to r, right? So up to the point r, this big R is the thickness of the wire, right? That is because from 0 to r, right, you have it is 0 right at the middle. Then as you build these circles, it goes, the enclosed current, closed integral B dot dl equals mu naught I. The I is the enclosed current. So the enclosed current is less inside from 0 to r, and after r there's there's just space, right? So the total current becomes constant from here onwards, from r all the way here, right? On this side the I is constant, on this side the I is changing. Okay, so for this is for r greater than capital R, where you're applying B dot dl equals mu naught I. Okay, and therefore you have peak B right on that surface. Okay, where is the B the most? The B is the most right on that surface. Okay, so that is the basic idea there. Okay, so inside, let's say if it was uniformly carrying Q, then you will find that you have to correspondingly here what he's saying, d phi by dt is this. Okay, it's proportional to r square, he's saying. So that's pretty much what I had in mind for the material that we are discussing with respect to um, um, the Faraday's law. Now I'm going to try and look at the next set of ideas which come right after Faraday's law, which deal with alternating current. Okay, so with respect to alternating current, let me okay, so we looked at B dot dA equals flux equals phi, and then we induced, we had phi equals BA cos theta of t, right? Therefore we had BA cos omega t, and then when you take the derivative, right, we had epsilon naught equals minus n times d phi by dt. D phi by dt was n dA omega sine omega t, if you remember from our discussion on alternating current with respect to the AC generator, right? So, and we said that AC generators produce a sinusoidal wave, right? That sinusoidal wave, when put in circuits, right, we have a peak voltage, right? Typically we discuss 2 or 3 different types of voltage. One is peak voltage, the other is RMS voltage. Okay, and then we also discuss the frequency of the voltage, linear frequency of the voltage, right? So the rate at which you rotate is the omega. Okay, now the rate at which you rotate is typically set for any geography, right? Here in America, we have what is called the rate at which we rotate is called the frequency, right? So the rate at which we rotate the the circuit inside the the magnets, right, in the AC generator is 50 hertz in America. So 50 times a second. It is, uh, I think, 60 hertz in India. The peak voltage is 220 volts, right? Or maybe the RMS is 220, right? Here we have 110 volts. The voltage is less. The peak voltage is 110 volts, and the hertz is also 50 hertz. So those are all different, but the ideas are the same, right? In how does alternative current? It produces a sinusoidal AC voltage. Okay, that sinusoidal AC voltage is transmitted across long distances to your home, right? And then in your home, you close the circuit. You have many different plugs, and from those plugs, you close the circuits, right? And when you produce a closed circuit, you end up with a alternating current. And so now that alternating current, right? So you have an alternating voltage which produces an alternating current, right? Now, if you had a purely resistive circuit, right? So if you had a resistive circuit, you have the voltage going like that, you have the current going like that. Okay. Now, this idea of the voltage and the current both changing at a fixed rate of 50 or 60 hertz is shown in what is called a Phasor diagram. Okay, many years ago they did not teach all this at in class 12, but they sure did teach it when you went to your first year in college. They would teach about this Phasor diagram. For a purely resistive circuit, the current is in phase with the voltage. What does that mean, in phase? It means that the ebb and flow matches. Okay, so the V and I are in phase, means that V and I, the peak of V matches the peak of I. The peak of the zero of V matches the zero of I. So in a resistive circuit, you will have an in phase voltage and current. Okay, so, and this is why they call it a Phasor diagram. Okay, now for a purely resistive circuit, they will be moving in parallel like that. So the phases will be moving, right? Now, if instead, if a purely resistive circuit, you had, a circuit which had an inductor or a capacitor as well in a alternating current circuit, right? Let me quickly tell you, a capacitor in steady state, right, would be like an open circuit in a direct current circuit which has a fixed voltage, right? There would be no current if you had a capacitor in a DC circuit. I hope I mentioned that, and I hope you picked up on it in our discussion with DC circuits, right? Anyway, if you missed it there, let me tell you here, okay? Now, if you had a inductor in a DC circuit, right, di by dt will be 0. Okay, a capacitor will act as an open. An inductor in a DC circuit will act as a short. It will have no resistance, in the ideal case, right? Typically, it will have some internal resistance, just like your capacitor also will have some internal resistance. Okay, so but the phi equals Li, right? So therefore, V equals L di by dt. If di by dt is 0, the V across the inductor will be 0, but it will behave like a short. Okay. Now, a capacitor, on the other hand, will behave like an open circuit. Okay. Now, they are always complements of each other, But if you put a capacitor or an inductor in an AC circuit, they will produce alternative currents with a change of phase. Okay, and we will go into the details of that in the next class. because I feel that if I go too far down this road today, I won't get to the very end, and I will leave you a little bit in lurch. But let me now explain average power, root mean square, and similar ideas. Okay. Now there is peak power, right? V equals IR V square. V times I will be peak in a purely resistive circuit at this point, right? That is peak power, right? Now, if you measure V times I over and you average it over this full area, V times I will give you the power. V times I is always the power. In a resistive circuit, the peak will be here, but what is the average, right? Or what is the root mean square power, RMS power? Okay, these are different, okay, for different circuits. Okay, now VI is when you, so how do you evaluate that? You integrate, right? How do you evaluate average and root mean square power? You integrate. Like, what is root mean square current? Is the square root of I square, right? And what is the average power? It is just I square R over the whole one cycle. Okay, so root mean square is 1 by root 2 times Im in the case of if the peak power is Im, this is I by root 2. Root mean square power is I by root 2, is about 70%, right? And therefore the average power is IRMS square times R. Okay, so these are the two ideas with respect to root mean square and average over one cycle, etc. Okay, so I am going to stop here for today, and I will start with a reintroduction of the AC circuit, and then take things from there, starting with the next class, and then I will try to make as much progress. We'll take another maybe 2 classes at least, I think, to get through AC circuits. But then I do feel that I would like to do some justice to the material there, and we can then look at how best to proceed from there. Okay, but as I said, the most important thing for you is to start doing more problems. Okay, we have now covered all the material with respect to magnetostatics, as well as all the material with respect to the chapter after magnetostatics. Okay, my suggestion is, which is basically Faraday's law and electromagnetic induction, including the ideas around AC generators. My question is that my request is that you download our app and you do questions. Do as many questions as you can, so that you build confidence around this material. This material is not easy. There are different various types of questions that they can ask, and I suggest that you understand what I say, but definitely learn some more from both the IIT PAL videos, which come with our app, and as well as by doing problems and questions. A person who builds his own knowledge base and who answers more questions is the student who is going to succeed, and you better start quickly and you better proceed forward, because I want to see all my students succeed. That's why I put this in front of you, and I try to re-emphasize it in every class. We want to see more of our students succeed, do well in all the exams, and go forward. And the key to that is assessment. First assessment is self-assessment. The second assessment is your teacher's assessment. The third assessment is only the exam assessment. Okay, so you got to first get through the self-assessment, then you will go to the teacher's assessment when in your own school and also elsewhere, and then you start doing the Jnana test prep assessments. We now have 10 tests available, and we are going to be adding more. We will eventually have 20 plus 20, 40 tests. 20 tests for the NEET students, 20 tests for the JEE students. So you will have quite a bit of tests. You can do 2 or 3 tests once you get going, right? But I know we are at the start of the year, right? That's why we are now emphasizing you to get going with the self-assessment. do questions on a chapter when you finish the chapter. So please do that. Say, download our app and get going with that. There is no better judge of how good you are as yourself. Do not rely on someday when the teacher will assess you. You assess yourself, you improve. All right. So download our app, use the assessment. All right. So I'm going to stop today's lecture. I will see you all next week.